Does anybody happen to remember what an angle in standard position is? It was taught last year. I know it was a long time ago. Angle in standard position.
Is that like when the angle comes from the mirror?
Yep. You talking about a graph?
Yeah.
Exactly. Very good. Draw a graph. Now, on the graph, put the vertex of the angle at the origin. One side of the angle must be pointing to the right side on the x-axis. The other side is pointing somewhere in one of the quadrants. This is called an angle in standard position. Vertex is at the origin. Here's just a quick little bit of terminology. Not super important, but I will use these words, so you have to know what I'm talking about. This is called the initial side. Okay. The other side of the angle is called the terminal side. Now there's two ways to measure an angle in standard position. If you start on the initial side and go counterclockwise in this direction, that's a positive angle measure. Counterclockwise is positive. We can also measure this exact same angle starting at the initial side and going clockwise. So that would give you a negative angle measure. So for every angle in standard position, there's two ways you can measure it. Counterclockwise would give you a positive. Clockwise would give you a negative. Now the reason that we draw these angles in standard position is so we can get an idea of the measure of the angle without having to use a protractor, because we don't have enough protractors to go around. So just a guess, your best guess, what would you say the measure of this angle from here all the way to here? How come we're in the hundreds already? From here to here is 90. Good. Why is it not, why are we saying 120, 130? Why not 190 or closer to 200? How do we know it's? Because there's 180. This is 270. This could either be 0 degrees or it could be 360 degrees, depending on how you look at it. So what are we saying, about 130 maybe, 135? Sounds about right. Put a Roman numeral 1, Roman numeral 2. This is how we number the quadrants, counterclockwise. Roman numeral 3, and a Roman numeral 4. Now, let's talk real quick about coterminal angles. Angles that share the same terminal side. This is something that you might remember from last year. I'd be surprised if you did, because I think just mentioned briefly. Angles that share the same terminal side. For example, I want you to draw these two angles on the same graph. Draw (200 degrees) Go ahead and draw that one, then I'll tell you the other one to draw on the same graph. So draw an angle that measures 200 degrees. Now, it doesn't have to be exact. You don't have to get a protractor out. You just have to make sure the terminal side is in the correct quadrant. And not just somewhere in the quadrant. It has to be as accurate as you can be. 200 degrees is it closer to the x-axis or the y-axis? That's what you need to decide. Where is that angle? Third quadrant? Closer to x, maybe by right there? And you have to draw that arrow going that way to show that you've measured the angle going in the positive direction. So there's 200 degrees. If I asked you now to draw this one, negative 160 degrees.
It's the same thing. You just drop the
What's the same? What do you mean?
It's the opposite. Negative angle.
So this one in red has the exact same picture. Is that what you're saying?
Yeah, but it's the arrow goes through the top.
Okay. So we don't have to draw a whole new angle because it would be in the exact same spot. We have to show that we've measured it differently. What are these examples of? Coterminal angles. Yeah, coterminal angles. Every angle is going to share the same initial side because everything starts by going along the x-axis here. The coterminal angles share the same terminal side as well. They're just measured differently. Okay. Let's try another one real quick. Draw a new graph. Draw a 400 degree angle. So where's that going to be? What quadrant are you saying there, Trent? First quadrant? How do we know that? Exactly. Good. 400 degrees means you have to go all the way around a circle once. There's 360 degrees. What's left over? About 40 degrees. But you do have to show with that little spiral that you've gone all the way around the circle once, plus a little bit more. So that's 400 degrees right there. What would be a coterminal angle for that? If I asked you to draw another angle on the same spot that's not 400 degrees. What about 40 degrees? What about 760? What about 760? It would go around twice, right? What if I went around 3 times and then added 40 more degrees? Would that be a coterminal angle? How many potential coterminal angles are there for that? Infinitely many. Now those are just the positive ones. Couldn't we go negative as well? Does anybody know a negative, or has anybody thought of a negative one? Negative 320. There's also an infinite amount of negative coterminal angles. They're all measured differently, but they share the same terminal side. 680, yep, negative 680. Is this ringing a bell? Does anybody remember this from last year? Coterminal, a little bit. Okay. So just write this down real quick. To find coterminal angles, what's a real quick and easy way? If I give you one angle and I ask you to find another one that's coterminal, what's an easy way to do that?
Add or subtract 360.
Yeah, add 360 going counterclockwise, or you could subtract 360 and go clockwise. Exactly right. To find coterminal angles, add or subtract 360 degrees. So in your homework, oh, by the way, I'll post that to the website tonight, what the homework's going to be. But on the homework, it's going to give you one angle, and then it's going to ask you for two coterminal angles, one positive, one negative. So add 360 or minus 360, whatever the case may be. Okay, pretty important topic here. Radians. So,
Here, press play here in a second. If you take a radius of any size circle, that represents a length, right? You guys watching this? If I took this length of the radius and wrapped it around the edge of the circle, that's equal to 1 radian.
check it out. They've got the radius. They take the radius, wrap it around the edge of the circle. That angle that's formed is 1 radian.
Okay. That's why it's called a radius, or radian from the radius. And it doesn't matter the size of the circle. If the circle expands, what happens to the radius? The radius expands, but it's still going to have the same measure of that radian. It's still going to cover that same portion of the circle. That's why with circles, radians are much easier to deal with, because it doesn't matter the size. 1 radian is 1 radian on any size circle.
How many radians do you think it takes to go all the way around? 6? Check it out. Half of a circle
is 180 degrees. But that's not quite 3 radians. It's 3 radians plus a tiny bit more. What number is that? It's 3 plus a tiny bit more.
3.14. Okay, 1 radian, 2 radian, 3 radians is right to here. If you add that little bit, that's 3.14159, that's pi. A half of a rotation is 180 degrees, or pi radians. So, you probably remember this a lot, because we did a lot of it in Algebra 2, but you're going to have to practice converting, going back and forth between radians and degrees. And this is the conversion factor right here. 180 degrees is the same as pi radians. Now, I'm sure you've done this year in your science class. Dimensional analysis or unit analysis. Remember doing stuff like that? Where you convert like feet to meters or miles per hour to feet per second. That's all just dimensional analysis. It's exactly what you're doing with radians and degrees. Let's convert. It's recorded. Convert degrees to radians. And the thing that you have to keep in mind is 180 degrees is the same as pi radians. Now, to keep it simple and to speed this up, you don't have to write the word radians. The lack of degree symbol right here implies that we're in radian measure, so I'm going to erase the word radians. 180 degrees is equal to pi. So, part A of this example, what's 120 degrees? Now, depending on how well you did in your science class on dimensional analysis, we're going to have to multiply this by a fraction, something over something. And the key is that fraction has to equal 1. That means it has to be something divided by itself. Isn't 180 degrees the same as pi? So if I took 180 degrees and divided it by pi, that's equal to 1 because they're the same thing. They're just measured differently, and we've got to put the correct measurement on this fraction so it'll cancel out the degree symbol. Where do I want to put the degree sign? Inside, but where? Why on the bottom? So the degree symbols cancel. But what's 180 degrees the same as? 1 pi, so I have to put the pi symbol up here in the top. So when you're going from degrees to radians, you put pi over 180. So the degree symbols cancel. Yeah. If we're going from radians to degrees, it's 180 over pi. So if you multiply straight across, you get 120 pi over 180. And then you simplify, you leave pi alone, but you simplify the fraction. 120 over 180. 12 over 18, which is 6 over 9, which is 2 over 3. So this is 2 pi over 3. So 120 degrees is the same as 2 pi over 3. And you don't have to write the word radians. By not putting that degree symbol, you imply that this is in radian measure. So try this one. 220 degrees. Go ahead and do that one on your own. 220 degrees. Same conversion factor. Because we're trying to cancel the degree unit of measure, on your conversion factor, the degree symbol has to be on the bottom. So the degree units cancel. You have 220 pi over 180. And then you simplify the fraction. 22 over 18 is 11/9, so it's 11 pi over 9 radians. Going the other way. Let's do a new example. Radians back to degrees. So if you give something like 7 pi fourths, it's in radians already. We got to convert it back into degrees. We're going to use the same conversion factor. We have to rearrange it because we're not trying to cancel the degree unit of measure anymore. We're trying to cancel the radian unit of measure. So what's it going to be? It's got to be 180 over pi so we can cancel the radian unit of measure. Was this 300 something? 300. 315 degrees. Yep, you can use calculators now. We getting the hang of this okay? Okay. Here's another example then. Find a positive and negative coterminal angle for this given angle. Theta equals 3 pi over 7. So we talked about positive and negative coterminal angles in degrees, but how do we do this when it's in radians? What are your suggestions? Let's talk about options. What were you saying, Diana? You can convert it to degrees. Once it's in degrees, how would you find negative and positive coterminal angle? Add or subtract 360. That would certainly work. That wouldn't be a problem if you did it that way. It is a lot of work because, you guys listening carefully, I don't want you to miss points on a test. I'm fine if you convert it to degrees. That's great. But if the problem starts in radians, you have to end in radians. So whatever angles you get in degrees, you got to convert those back into radians at the end. Are you listening carefully? You can do it. It's a lot of work. Is there an easier way? just leave it in radians. And instead of adding 360, you add 2 pi. Why 2 pi? Yeah, half of a circle is 1 pi. A full circle is 2 pi. So I would, if it were me, I would just leave it in radians rather than converting to degrees and then converting back into radians at the end. It'd save you time. So just add or subtract 2 pi. So I'm going to take 3 pi over 7 and add 2 pi. That will give you a positive coterminal angle. As long as, I guess, you guys can add fractions, which by now I hope you can. Even without calculators, this shouldn't be a big deal. How are we adding this? It's got to be 14 over 7. Yep. 2 pi is the same as 14 over 7 pi. Got to get a common denominator. 3 pi plus 14 pi is 17 pi over 7. So there's the positive coterminal angle, 17 pi over 7. To find the negative one, just keep the same fraction, 14 pi over 7, and subtract it though. Do 3 pi over 7 minus 14 pi over 7. And subtract. Negative 11 pi. Positive and a negative coterminal angle. Let's go to the next subtopic. Arc length. And the area of a sector. Alright, do your best to draw a circle. Make it kind of a larger one because we've got to draw some things inside of it. If your circle's not as good as mine, that's alright. I've practiced. You guys are jealous. Check that out. You're better than this one?
Come check out my circle.
I don't want to make you guys feel bad.
Would you be jealous?
Tell you it's not as good as this one. So locate the center of your circle. Locate the center, place a point there. Okay, now draw a radius. And draw a second radius. Hopefully this is an obvious question. What's the measure of both of these radii? Well, what if I told you the measure of one? What would the other one be? They're both the same, right? I hope that was obvious. Yeah, that's true. If you added the two. Now, it's important that this angle is in the center. This has to be a central angle. Now, place the symbol theta there because we're not sure exactly what the measure of that angle is. Now, from one end of the radius, I want you to trace around the outside edge and end at the other end of the radius. If you trace around the outside edge of a circle, it's called an arc. In particular, this is a minor arc because it's less than half of a circle. If it's more than half of a circle, it's a major arc. If you go all the way around a circle, what kind of an arc is that? A circumference? Is that what you're trying to say? All the way around a circle is a circumference, right? Okay. Now, for some reason, arc, the symbol is S. So when you see the letter S, they're talking about arc length. Yeah, I don't know. Arc length is what S stands for. Really easy formula. It's the radius times the angle. So whatever the length of the radius is, you multiply that by the measure of the angle. Now this is critical that you make a note of this. Theta is in radians. This formula only works when theta is in radians. Now, as neatly as you can, bold in this portion right here. As long as the angle stems from the center of the circle, and this is important, again, this angle has to be a central angle. But as long as that angle is a central angle, that portion is called a sector. A for area, it's not quite as an easy formula, but you are going to have these two memorized that won't be given to you. The formula is 1/2 times the radius squared times the angle. And again, make the same note, theta is in radians. Quick example. Okay, there we go. So put the radius as 11 feet. The angle is 30 degrees. On the arc length for part A. Go ahead and give her a try. What's the first thing you guys did? Degrees has to be radians. Okay, you cannot use the formula unless it's radian measure. So 30 degrees. What is that? Pi over 6. Yeah. 30 degrees is the same as pi over 6 radians. You had to make that conversion. Now you can use the formula S equals radius times theta. Radius is 11. Theta is pi over 6. So it's 11 pi over 6 feet. Technically, we have to include the unit of measure. 11 pi over 6 feet. And now that we know that the degree measure is pi over 6, part B here ought to be easy. What's the area of the sector? So we use the formula, area equals 1/2 times the radius squared times pi over 6. So it's 1/2 times 121 times pi over 6. And how do we combine all of this? Keep it in exact form, not estimating. Exact form means you don't multiply pi in there. You leave pi as part of the answer.
5.5 pi.
Okay. Leave it as a fraction also as well. Yeah. These are all fractions, you guys. How do you multiply fractions? Straight across, right? So it's 121 pi over 12. Then you got to figure out if 121 over 12 simplifies. Nothing goes into, I think that's as far as it goes. Now, what's the unit of measure? It's feet squared because it's an area. You measure area in square feet or square miles or square inches or whatever the unit of measure. But okay, that's arc length and sector area. Again, I know we're not doing a ton of examples, but you've done all this last year in your Algebra 2 class. This next part, circular motion. We're going to start with it. We'll have to pick up with it again next time. I don't think we'll be able to finish it all. Circular motion. So draw another circle.
I don't like it when this is all up.
It makes you better at drawing circles.
Yeah, I want to be better at drawing circles.
Now, imagine that this point is moving around the edge of the circle. There's two ways to describe its speed. Two ways to describe the speed of this point. We can talk about what's called its linear speed. This is the kind of speed that you're used to. It's well, what's the formula for calculating a distance compared to a rate and a time? Distance equals rate times time. So this linear speed formula is a derivation of that. Distance equals rate times time. Now, if I want to talk about the rate or the speed, how do I get rate by itself here? Divided by time, right? So rate would equal distance over time. Now, particularly on a circle, how do we describe the distance around the outer edge? We just talked about it. What's that called? All the way around would be a circumference, but what if it's only a portion? That's the arc length, right? So the linear speed, which we're going to call v for velocity, the linear speed velocity is equal to, instead of distance, we're going to call that s. Why s? That's the arc length divided by time. So its linear speed v is described by how much of an arc length it travels divided by how long it took to travel that arc length. S over t, that's its linear speed. Okay? That would be given in something like feet per second or miles per hour. It's some kind of a linear distance divided by a unit of time. How else could we describe the speed of that object if it's on a circle? What do circles do when they're moving? They spin, right? You guys heard of RPMs? What does RPM stand for? Revolution per minute. Is that a linear speed? What does revolution per minute mean? It's how fast. It's not how fast it's moving per se. It's how fast it's turning. It's how fast it's spinning. That's called angular speed. RPM would be an example of an angular speed because it's not talking about feet per second, or it's not talking about miles per second. It's talking about revolutions per minute. That's how many times it turns, given a unit of measure. So angular speed is given by the Greek letter omega. It looks like a W, but it's a Greek letter. Omega. Omega is equal to not S for arc length, but theta for angle measure. How many radians does it turn divided by any given unit of time? These are two ways to describe the speed of a point moving around a circle. Angular speed and linear speed. Yeah.
So is angular speed always in radians?
Yep. Yep. That's got to be in radians. You may use these two formulas once in a while, okay? But this one here, the relationship between linear and angular speed, you're going to be using this one a lot. So let's actually derive the formula. It might help you remember it better if we can derive it. V is equal to S over T. That's just the linear speed formula, right? But what is S equal to? So what is it equal to? Radius times theta, right? But S is equal to radius times theta. So we can amend this formula here. Instead of V equals S over T, couldn't we call it V equals what over what? Help me out here. R times theta all over T. Now, where do we recognize this? Look on your notes. That's angular speed, right? Theta over T is just angular speed, so we got to do one more change to this formula. V, the linear speed, is equal to the radius times omega. This formula you're going to be using quite a bit. This is a formula that relates linear speed to angular speed. V equals radius times omega. So the bell's going to ring in about a minute, so we don't have time to go into this problem. But the problem we're going to do on Wednesday, listen carefully. Okay, let me just read it to you. I want you to think about it. A woman's riding a bike. The radius of the tires are 26 inches. The wheels rotate at 125 RPMs. How fast is she going? How fast is she traveling? Those are the kind of problems we're going to have to do. Okay. We'll pick that up next time.